As we go through the S-curve adoption of electric vehicles, there's a lot of people coming into the community that are new. And if you all are like me, you probably purchased the electric vehicle understanding that it has batteries and electric motors, but weren't up to speed on the same level as internal combustion engine components with what is the underlying technology. This video is just a quick primer on electric vehicle technology to kind of help people who are new to electric vehicles get up to speed. When I was going through high school, I had auto shop, and I learned about the battery chemistry and the cranking power of a battery, internal combustion engine components, struts, shocks, things like that. So I feel as though I've got a pretty good understanding of internal combustion engines. But as I started to venture into EV ownership, I realized I really didn't know much about the underpinnings of the electric vehicle technology. And here's just a quick run through of the basics. There's two different types of motors. One is a permanent magnet, the other is an induction. The difference being a permanent magnet motor has magnets actually in the rotor. Sometimes they're embedded in the rotor, and sometimes they're floating on the outside of the rotor, but permanent magnet has actual physical magnets on the rotor. An induction motor has these coils, and it induces a magnetic field without magnets being present. The way this works is permanent magnet motors are the ones that can do the regen effect where when you're slowing down, the electricity is getting generated and being put back into the battery pack. Induction motors can't do that for some reason. I think it has to do with the fact that the field is being generated through electricity or something. I'm not exactly sure the specifics of that, but I know induction motors can't do regen. There are some cars that have two induction motors but can still do regen, but they're not regenning off the motor. They're regenning off a different device. I think Audi is one of the ones that is able to do that. But normally the way it works, if you have an induction motor, it's on what's known as the secondary axle, and the primary axle is a permanent magnet motor in order to do the regen. And then the induction will be on a secondary axle, and sometimes in commercial applications, they have induction motors on every wheel, and maybe just one permanent magnet motor. So 3 induction and 1 permanent magnet. It varies, but the point being is that most EVs nowadays have permanent magnet motors. If your car does have an induction motor, it's likely on a secondary axle. Okay, so batteries. The most common are cylindrical, and it's, we all have batteries sitting around our house, and the cylindrical batteries are not too different from this. In Tesla terms, there was something called a 2170 cell, which is the most common cylindrical battery. And the 2170 number comes from 21 millimeters of diameter and 70 millimeters of height. So it's not too large of a battery. You just stack them in there and make sure they fit close to each other, and off you go. But you could imagine, this is pretty heavy. When you really start to stack a lot of them, it becomes expensive and heavy. The battery pack is the most expensive part of any electric vehicle. It's basically, if it needs to be replaced, it's like replacing the transmission and the engine block all at once in comparable pricing. Prismatic is another form factor. And the most common one nowadays is what's called LFP. If you have LFP batteries in your car, one of the nice things that you can do is charge it to 100% every day without having any fear of degrading the battery pack. If you have cylindrical or polymer or pouches, the polymer are also called pouches, you want to charge to 80 or maybe 90%, depending on the manufacturer's recommendations. My Volvo, they say you can charge it to 90, and it has to do with how much residual is in the battery pack. But anyway, you don't want to charge to 100% every night unless you have LFP batteries. And there's a few cars out there that have LFP, and if you own one of them, you can charge it to 100% every night and not have to worry about it. Inverters. So we have motors, we have batteries, and then the most important piece of an electric vehicle is the inverter. There are two different kinds of inverters. There's IGBT, which stands for, let me get my notes here, IGBT, isolated gate bipolar transistor. And then there's the silicon carbide, which is also a transistor. But the silicon carbide costs more, but it handles the heat better. And what's going on here is that we in the United States, since back in the Thomas Edison days, where he was a proponent for direct current or DC electricity distribution, and Nikola Tesla was a proponent for alternating current transmission of electricity. Just because alternating current can be transmitted further with less loss, the country went that way. And we've been using AC ever since, except for into a few niche cases like telecommunications equipment in certain circumstances use direct current. Anyway, the battery pack is direct current, and we need to invert that for the electrical motors into alternating current. And that's what the inverter does. Silicon carbide does so more efficiently, but it costs more. But because this is such a vital piece of the electric vehicle, we're seeing adoption of silicon carbide inverters starting to take hold, which will drive the price down and basically make it probably common in the coming years. We'll just see silicon carbide. So two different types of inverters, the IGBT or silicon carbide. Next thing I want to go over is you're going to have to charge your car out there in the wild eventually, and you're going to be confronted with one of these DC fast charging networks. So let's go over the technology in those. EVgo uses primarily DC fast chargers from a company called Delta, and they're very characteristic. There's cable management and this kind of shape that has the arms on the sides like that, so very recognizable. This is a 350 kilowatt dispenser. The actual charger is off to the side, but this is a 350 kilowatts, and so both handles can be used at the same time, which is pretty cool. They split the power between the 350, 175 per handle is available if both are in use. Otherwise, 350 in use is available for one handle if that's all that's in use. These are also Delta chargers, but these are 100 kilowatt Delta chargers, but also commonly seen. Normally what you'll see at a EVgo station is, one or two of the 350s and then a collection of these 100 ones. So they make it available for different types of electric vehicles out there. And if you have a car that can't do 150 kilowatts like a Nissan Leaf or a Chevrolet Bolt or older model EV, Hyundai Kona electric that can only do, I think, 80 kilowatts, you probably want to stay on the 100 ones just to be courteous for people who are coming in with newer EVs who need to get a faster charge. EVgo also has these Signets, and if you look right up here, it says Signet. The difference here is that each dispenser can only charge one car at a time. Even though it has two handles, only one of the two handles can be in use at any given time. Electrify America is basically standardized on those same Signet chargers. Again, each dispenser can only charge one car at a time. So even though there's two handles on Electrify America stations, you can't charge two cars at a time. It's only one dispenser, one car. These ChargePoint DC fast chargers are called the ChargePoint Express 250s or CPE 250s. They dispense at 62.5 kilowatts. There are newer models that can dispense faster, but these are all over the place, and lots of times they'll be wrapped in marketing wraps for local co-ops or electric companies. But you'll recognize up here, it'll say ChargePoint, and these swivel arms are a good way of recognizing them. Tesla makes their own, and they come in 4 generations: Gen 1, Gen 2, Gen 3, and Gen 4. The main difference is once you get to Gen 3, the cables are liquid cooled, and they speak the CCS standard. So any Gen 3 station are the ones that are going to be open to non-Teslas in the coming months here. If you come up to a Tesla supercharger station and it's Gen 1 or Gen 2, you can't charge a non-Tesla at those locations. So that's the main difference. ABB is making chargers now that are getting put in by Circle K at 180 kilowatts. Those are the Terra 184CJ chargers, if I remember correctly. This one over here is much more common. You'll see these at dealerships. This is the ABB Terra 54 HVC. Very common at dealerships. And most of the time dealers will make these free because the payment system is a little bit kludgy. This one pictured here is at Nissan of Hickory, North Carolina, and it is made free to the public. FreeWire has something called a boost charger. This thing is a ton of fun. Its claim to fame is that inside this cabinet is not only a DC fast charger, but batteries. So a site host doesn't need to get a service upgrade in order to put a FreeWire boost charger in. They just connect it to a normal 240 volt 100 amp circuit, and it will fill up the batteries and then dispense from the batteries. One thing you have to keep in mind, if you pull up to a FreeWire boost charger and it was heavily used prior to you showing up, it might have the batteries depleted, in which case you're only going to get 19.2 kilowatts from the 100 amp 240 volt connection to the breaker panel inside the site host's facility. But if you pull up and the batteries do have some juice in them, they'll dispense pretty good. I think it's right around 150 kilowatts that these will dispense at. So it's a good alternative. Anyway, just to review, three main components are the motors. You got permanent magnet or an induction. The batteries, you have cylindrical, prismatic, or pouches, and the inverter, which is IGBT or silicon carbide. Hope this helped.